Welcome to the PID Settings page. In this section, the user has access to a multitude of settings and parameters that can be used to customize the system's responses for a particular process. The available settings are determined by the system's configuration. For instance, if the system lacks a flow meter, the PID control settings may not be accessible to the user. Starting at the top of the page, we find the fluid density setting. This feature is particularly beneficial for systems without a flow meter or those equipped with a co-solvent pump. The pumps are calibrated for mass flow using water as a standard, which has a density of 1 gram per cubic centimeter. However, compressed liquids like carbon dioxide and ethanol do not have densities of 1. Their densities are lower, so without adjusting for this difference, the pump would deliver less mass than expected. This setting allows the user to adjust the density according to the particular fluids in use, which automatically alters the pump speed to compensate. Flow meter control includes the settings that affect how the pump responds to the flow rate, as recorded by the flow meter. When available, the PID settings can be adjusted. These settings influence how the pump reacts to variations in carbon dioxide density and changes in the flow rate. PID stands for Proportional, Integral, and Derivative Response Calculation. These settings should be adjusted only if the user is knowledgeable about tuning this calculation. The sample interval setting specifies the duration between PID calculations, measured in milliseconds. It dictates the timing for applying these calculations as the process advances, serving as one of the parameters that can alter the system's response speed. The deviation limit is measured in grams per minute, and represents the variance between the set point, SP, and the process value, PV, as reported by the flow meter. If the flow meter's readings surpass this value, the system may deduce a potential issue with the incoming carbon dioxide supply. If this deviation is reached, the pump will switch to computed control as a precautionary measure, ensuring that the pump does not operate at full speed when there is no carbon dioxide flow. The duration for which this deviation can persist before the system transitions to computed mode is referred to as the deviation time, and it is measured in seconds. In pump pressure mode, the pump aims to reach a predetermined pressure, disregarding the flow. This specific mode can be chosen both from the dashboard and within the recipe section. When the pump is in pressure control mode, the PID settings can be adjusted from here. As with flow meter control, the sample interval setting specifies the duration between PID calculations. This control panel manages the automatic back pressure regulator. These settings form the basis of the core separation adaptive pressure control. Every setting is crafted to control the pressure in the system with precision and accuracy. The settings included with the systems are calibrated to accommodate a broad spectrum of process conditions. Nevertheless, our systems are adaptable, and provided the user has the capability to fine-tune the PID settings, the system can be specifically adjusted for a desired response to a particular process. We begin with the compression zone, measured in bar. This accounts for varying compression rates when transitioning from liquid to a supercritical phase. The indicated level determines the point at which PID control initiates. Below this number, the PID receives a static value, as determined by the compression zone PID output setting. However, if the process requires liquid carbon dioxide, such as pressures below 74 bar, this setting should be altered to allow the system to achieve the necessary set point. As previously mentioned, the sample interval measures the duration between PID calculations. The set point ramp rate dictates the target ramp rate for the ABPR to control. It manages the progression of the set point in predefined steps and is measured in seconds. The pause set point ramp function, used in conjunction with the set point ramp rate, serves to suspend PID calculations when a deviation in the ramp rate is detected. For instance, if the set point ramp is configured for 1 bar per second, the set point would shift from 55 bar to 75 bar over 20 seconds. If the pause function is set at 15 bar, it would permit a deviation of up to 15 bar between the set point and the process value before pausing the set point ramp. This allows the system time to align with the intended ramp rate. This mechanism manages the error between the set point and the process value in the PID calculation, enabling more precise control over the pressure buildup. This works for pressurizing and depressurization stages. The output ramp rate is the highest permissible response by the ABPR for each PID calculation. For example, a setting of 1% implies that at each calculation, the ABPR needle is limited to moving only by 1%, regardless of the outcome dictated by the PID calculation. Finally, the SP overshoot limit comes into play when the process value strays from the internal set point. This deviation event will stop the system, as it could indicate a problem such as a blockage. The PID settings are split into 5 zones. Each zone permits the user to apply a different PID response. The zone SP delta specifies which calculation should be used, based on the value of the process relative to the desired set point. For instance, if the process value is 20 bar away from the set point, the system interpolates the PID calculation between zones 2 and 3 to ascertain the appropriate response. This facilitates different responses as the process value begins to approach the desired set point. These zone calculations have now been superseded by the addition of the Setpoint ramp feature. The heater settings, found beneath the adaptive pressure control block, govern the behavior of each heater equipped with an electrical heater band. We begin with the heater zones. These zones function similarly to the pressure control zones, enabling the user to input varying PID responses depending on the situation. Similar to the setpoint ramp in pressure control, the temperature ramp rate controls the setpoint ramp for each heater. Working in tandem with the setpoint ramp is the setpoint pause, which functions as previously described. Unlike the ramp in pressure control, the heating ramps are only operational for temperature increases, not for decreases. Similar to earlier settings, the sample interval controls the duration between PID calculations for the heaters. The cycle interval represents the combined on and off time for the heater before it repeats. For instance, if the cycle time is set at 1000 milliseconds and the PID output is 40%, the heater will be on for 400 milliseconds and then off for 600 milliseconds. This cycle is continuously repeated throughout the process. Finally, the PID output dictates the maximum power output permissible for the heater. For example, if the heater is 2 kilowatts and the maximum output is set at 50%, then the heater can only attain a maximum of 1 kilowatt of heating, limiting the amount of heating the system can produce.